So welcome to lecture 3.7, Indeterminate Forms and LHospitals Rule. This week I decided to go with a new hairstyle. I would welcome any feedback. How do you think it's looking? I'm thinking about bringing back what would that be? The 14th century maybe? Anyway, let's look at LHospitals Rule. This is, by the way, the Count de l'Hôpital. So the first thing we need to understand is the concept of an indeterminate form. Recall earlier that when we were doing limits, even though some functions and equations might not be defined or continuous at some point, we could still evaluate a limit as x goes to that point or as x goes to a, either graphically or analytically. For example, remember when we looked at the limit as x goes to 1, here if we plug this into the denominator goes to 0, so it means that this equation is not defined at 1. But remember when we factored the numerator and denominator, we could see that we had a common factor of x minus 1 that we could cancel out, excuse me, and when we did that, we could see that the function actually gets closer and closer to 1/2. And so remember, that's what our limit concept is what is the value we're getting closer to as x is getting closer, in this example, to 1. So in general, if we have a limit of a rational function where both the numerator and denominator go to 0, notice that is the case here. If I plug in 1 in the numerator, I also get 0. 1 squared is 1 minus 1. When we have the case where both the numerator and denominator go to 0, again as we have up here, then this limit may or may not exist. And this is the first indeterminate form. So again, the indeterminate form here is 0 over 0. So we have a quotient. When we apply the limit, both the numerator and denominator go to 0. This is the indeterminate form of 0 over 0. Okay? So this again is the first indeterminate form when both the numerator and denominator go to 0. Now notice we're handling these differently. We're not handling this as one big problem or function. We're saying if I put this in the numerator, does it go to 0? When I put this in the denominator, does it go to 0? Not does the whole equation go to 0, but each piece. Did the numerator go to 0 and the denominator go to 0? Okay? Another type of issue can occur when we're looking for horizontal asymptotes. Remember, at large values of x, by evaluating that function at infinity or negative infinity. And notice here, this is a previous example we did as well. We get infinity minus 1 in the numerator, infinity in the denominator. So it's not really obvious how to handle this limit or what may occur since both the numerator and denominator become large. And so here you might think of it as a contest to see who grows fastest or who becomes largest quickest, and they're the winner. Okay, think of it that way. If the numerator wins, that means the numerator is getting bigger faster than the denominator, then we have no limit because it's going to infinity. If the numerator is larger than the denominator, then the whole function is going to infinity. If the denominator wins, if the denominator is getting larger quicker, then the limit goes to 0 because you have a smaller number over a much larger number, and again that's going to 0. Again, think of 1/2 versus 1/1000. From 1/2 to 1/1000, we're getting closer and closer to 0 or to a smaller number. Or maybe we have some kind of tie, and by a tie here we mean that the numerator and denominator are growing in some form of ratio, and that constant ratio would then be the limit. Okay, sorry about that. So before we analyzed this specific problem analytically, we divided the numerator and the denominator by x squared, or multiplied it, each piece by 1 over x squared. Again, we haven't changed the functional value since we're multiplying numerator and denominator by the same thing, 1 over x squared over 1 over x squared. We're actually multiplying by a factor of 1, which is how we find equivalent fractions. And so when we did that, we could see that both of these pieces, 1 over x squared and 1 over x squared, go to 0 as x goes to infinity, and that was kind of the rule we used for solving these limits at infinity. So this form is known as the indeterminate form of infinity over infinity. So now we have two forms. If the numerator goes to 0 and the denominator goes to 0, that's 0 over 0, the first indeterminate form. If they both go to infinity, then we have the second form of the second indeterminate form of infinity over infinity. Okay, so you need to be able to identify if there is an indeterminate form. And again, that's plugging in the value of the limit and seeing what happens to the numerator and what happens separately to the denominator. If you have infinity over infinity or 0 over 0, you have what's called an indeterminate form. So the examples we've looked at were actually quite easy to evaluate analytically, but some functions are not easy to evaluate graphically or algebraically. Okay, and so there's an alternative method known as LHospitals Rule, and it says if we have a limit of indeterminate form 0 over 0 or infinity over infinity, then the limit of the original function of f of x over g of x, the limit of that quotient, is actually equal to the limit of the derivatives of the numerator and the denominator. This is quite crazy, and it's kind of cool. It's another one of those magical places in calculus where the derivatives help us solve something that was quite difficult to solve before, and it's like a shortcut. Okay, now of course the limit has to exist, or it has to be infinity, which means it really doesn't exist, but we'll talk about that later. So again, all this is saying is that the limit of a quotient of functions, where's my mouse? There we go. The limit of a quotient of functions, the limit of a quotient, is equal to the limit of the quotient of their derivatives, provided that the given conditions are satisfied. Okay, now the given conditions it's talking about is that you have an indeterminate form. Okay, so you can only apply LHospitals Rule, you can only take the derivatives of the numerator and denominator after you've checked the original function and made sure you had an indeterminate form. Okay, so you have to apply that first. Note 2 just says that this is valid even if you're looking at one-sided limit. So if this is going x to a plus and you still have 0 over 0 or infinity over infinity, you can still apply LHospitals Rule. So let's look at the first example that we had done way back in, I think, chapter 1 with limits, and see what happens. Now again, remember we said that we do have 0 over 0. When we plug in 1 into the original equation, where'd my mouse go? There we go. When we plug in 1, we get 1 squared minus 1, 1 squared minus 1, over 1 squared minus 1, which gives us 0 over 0. This is the first step always in applying LHospitals Rule. Now, then if we have that, then we can apply LHospitals Rule by taking the limit of the numerator and denominator. Actually, that's the wrong word. This should say take the derivative of the numerator and denominator separately. Okay? This is not the quotient rule. I'm not trying to get you to take the derivative of the entire function. You are taking the derivative of the numerator and you're taking the derivative of the denominator separately, okay? So this is much, much simpler, okay? So don't overcomplicate this by trying to apply the quotient rule. This is not the quotient rule, okay? So the derivative of the numerator, notice, is 2x minus 1. The numerator is x squared minus x. The derivative of x squared, 2x. The derivative of minus x is minus 1. The derivative of the denominator, x squared minus 1, is simply 2x, because remember the derivative of a constant is 0. Okay? So then we plug these in. The derivative of the numerator is here. The derivative of the denominator is here. I don't know where that guy went. And we can see that now when we plug 1 in, we get 2 minus 1 is 1, and 2 times 1 is 2, and we get 1/2, which is the same value. Okay? Now, one of the things that you don't see here, because I don't have this notation, is typically when we're applying LHospitals Rule, what we will do here between the original equation and the application of LHospitals Rule is instead of an equal, we'll have an equal with a little h on top. Okay, so putting an h on top lets you know that you're applying L'Hopital's rule to this next piece. All right. Hey, this works. It's part of that magic of calculus, and maybe it's worth something, maybe a little bit of money. Well, this is a little bit of math history, and in fact it was. This is L'Hopital, Guillaume François Antoine Marquis de L'Hopital. So I said 14th century. This looks like it was actually the 17th century, which of course that was kind of stupid. I mean, calculus wasn't even identified until later. Sorry about that. Obviously he's a count or a marquis, and he was well-to-do. He was pretty good at math, but he wasn't quite the epitome of math at that time, but he did have money. And so what he did is, often wealthy intellectia would have private tutors. One of his tutors in math was Bernoulli, an exceptional mathematician of the time, who actually proved this theorem. And this theorem, what I'm trying to say, is actually Bernoulli's theorem, but L'Hopital bought it from him so he could put his name on it. He wanted to live in infamy in the world of math, and so he actually bought the theorem. This is funny. This was actually some notes I had put on this slide a couple years ago, well before our election of 2016, which I thought was kind of funny, that since he bought the forum and he has a bad wig, maybe he would be the Donald Trump of math in the 17th century. All right, let's look at another example. Let's get back from our little commercial break in the History Channel here. So again, remember, this is an example. We already know the answer, so we just want to look at it. Always, always first we're checking for an indeterminate form. Plug in the value of the limit. This time we're plugging in infinity. X goes to infinity into the original equation. Infinity squared minus 1, 2 infinity squared plus 1, and notice this just gives us infinity. Okay? So we have the indeterminate form. So now we can take the limit of the numerator. Again, we're doing these separately. X squared minus 1 becomes 2x. 2x squared plus 1 becomes 4x. And now we apply L'Hopital's rule. Again, it would be really good to have a little h here, and I don't have that little h, sorry. Okay? Knowing that as we move from here to here, we're applying L'Hopital's rule. Good form is to put an h above the equal so we know what we're doing. Notice what we have here is L'Hopital's rule. The derivative of the numerator over the derivative of the denominator, and again, we are not applying the quotient rule, we're applying derivatives of each piece. Notice when we have put the limit in, we're back to infinity over infinity. Okay? And we still have an indeterminate form. And one of the nice things about L'Hopital's rule is we can apply it multiple times. So we can take the second derivative, or just take the derivative again, of both the numerator and the denominator. But we can only do that if after we've taken the first, after we've applied L'Hopital's rule one time, we also have an indeterminate form. This only works if we still have the indeterminate form of 0 over 0 or infinity over infinity. So let's apply L'Hopital's rule again. So the derivative of the numerator is now 2, right? The derivative of 2x is 2. The derivative of the denominator, 4x, is 4. So we can apply this, L'Hopital's rule, a second time, and notice what we have here is a constant, and it matches what we found. So L'Hopital's rule is iterative, meaning as long as we still have indeterminate forms, we can apply it again and again until we get to a simpler version of the problem. And it may be that we still get to infinity. All right, now I'm going to work through these a little bit faster. What I would suggest is this is a great place to pause. I would also remind you that you can see that there are videos here for each of these problems. These are both from your online text, your e-text, so you can go in and watch someone else do these as well, which they'll probably take a little bit longer. Okay, so the first thing we want to do is, do we have an indeterminate form? Well, as the natural log of 1, the log of 1 is always 0, so as we're getting closer to x being 1, we're getting closer to 0. 1 minus 1 is also going to 0 as x goes to 1. So we have 0 over 0. We do have the indeterminate form. So we take the derivative of the numerator, take the derivative of the denominator. The derivative of the log of x is 1 over x. The derivative of the denominator, x minus 1, is simply 1. And so we have the limit as x goes to 1 of 1 over x, which we can now just apply the 1 because it's continuous, and we get 1. So this limit actually goes to 1. Let's check here. Again, the first stop is, do we have an indeterminate form? When we plug in infinity as x goes to infinity into e to the x, e to the infinity is infinity. Infinity squared is infinity. So we have infinity over infinity. So we do indeed have an indeterminate form. So we can apply L'Hopital's rule. The derivative of the numerator, the derivative of e to the x, is just e to the x. We learned that in the last chapter. The derivative of x squared is 2x. Okay. Notice here, when we put infinity in, we still have e to the infinity, which is infinity, over 2 times infinity. So here we still have infinity over infinity. Okay? So we apply L'Hopital's rule again. The derivative of e to the x is e to the x. The derivative of 2x is just 2. Okay? Notice now we have infinity, e to the infinity, which is infinity, divided by 2, which is still infinity. We cannot apply L'Hopital's rule again because we do not have an indeterminate form. We have infinity over 2. Infinity over 2. We do not have infinity over infinity, so we're done. So we say that this limit equals infinity, which we talked about this before, which really means that the limit doesn't exist. Okay? So here we applied the rule twice, and the limit did not exist, or you can say it goes to infinity, which is explaining how this limit doesn't exist. It just keeps growing and growing. Alright, again, I suggest you do a pause here and see if you can solve these. Do we have an indeterminate form? So we have the natural log of infinity. Well, we'd have to have an exponent of infinity on e to get to infinity, so the numerator is definitely infinity, and the cube root of infinity is also infinity. So we do have the indeterminate form of infinity over infinity, so we can apply L'Hopital's rule. The derivative of the natural log of x is 1 over x. The derivative, now be careful here, this is not x to the negative 1/3. We're just taking this as a function in itself, so it's x to the 1/3 in the denominator. We're not thinking of it as negative yet. So when I take the derivative of x to the 1/3, again, it's not x to the negative 1/3 because we're considering each piece separately for L'Hopital's rule. We're just looking at this function, which is x to the positive 1/3. So we get 1/3 x to the negative 2/3. Okay. So notice this gives us, when you simplify this, the x goes in the denominator, the x to the 2/3 goes in the numerator, and when we subtract those exponents, x to the 1 power, x to the 2/3 over x to the 1, we get this piece here. This may be a good one to look at the video because they may walk through the steps of how this simplifies, and sometimes this throws people off, but it's just the exponential rule, right? We can see that the x in the numerator, 1 over x, means that x will go to the denominator. 1/3 is in the denominator. Since it's a fraction in the denominator, it will also be reciprocated. Wherever there's a fraction in a piece, the fraction in the numerator sort of gets reciprocated, which means the x goes to the denominator. The fraction in the denominator also gets reciprocated, which means the 3 goes up top. And again, when you have a negative exponent, it goes up top. So you have x to the 2/3 over x, which actually gives us x to the negative 1/3, or the cube root of x in the denominator. Alright, so once we are here, notice we do no longer have the indeterminate form because we have a constant in the numerator. But the denominator still goes to infinity, so this limit goes to 0. Okay. Notice we could have applied L'Hopital's rule twice here, because this goes to 0 and this goes to 0, But it just seemed to be easier to simplify it algebraically or analytically instead of trying L'Hopital's rule again, especially here when we'd be getting into more complex exponents and negative exponents. All right, let's see what's happening in example 4. Remember, the tangent is 0. The tangent of 0 is 0, excuse me, minus 0. So we have 0 in the numerator. 0 cubed is also 0. So we have 0 over 0. We have an indeterminate form. Okay. So when we take the derivative, again we're applying L'Hopital's rule. The derivative of tangent is secant squared. The derivative of negative x is negative 1. The derivative of x cubed is 3x squared. Okay. Secant, remember, is 1 over cosine. Okay. So here we have 0 in the denominator. Here we have the 1 over cosine. The secant at 0 is also 1 because cosine at 0 is 1 and 1 over 1 is 1. So we get 0 in the numerator because we have 1 minus 1. So we have 0 over 0. We have gosh, I went blank there. We have a indeterminate form of 0 over 0 still, so we apply L'Hopital's rule again. Alright, so the derivative of secant squared, this is a chain rule, right? So 2 times secant x, this should be secant x, it shouldn't be secant squared x because we would drop the exponent. So this 2 is misplaced here. It should be 2 times the secant x times the derivative of secant x, which is, secant tangent, my bad. So 2 secant times secant tangent would give us secant squared. So that exponent of 2 is exactly right, my bad. All divided by the derivative of 3x squared, which is 6x. Okay. So when we look at this again, notice we can, first of all, pull out the constant, 2 over 6, which is 1/3. The derivative of secant is 1 times the derivative of tangent, which is 0. So we get 0 in the numerator and 0 in the denominator. So we still have an indeterminate form, 0 over 0. Okay? When we apply the derivative again, we get 1/3 times the limit of simply tangent x. Wait, that's not true. We didn't apply that derivative again. Secant squared x tangent x. Now, why am I not seeing this? When we simplify this, it just goes down to tangent x, but that doesn't make any sense. One over cosine squared, sine squared over cosine squared. Now, how did you get to tangent x from? Okay. Notice, now I'm thinking straight. Notice that we could pull these out separately, and we could evaluate 1/3 times the limit as x goes to 0 of secant squared x times the limit as x goes to 0 of tangent x over x. Well, the limit as x goes to 0 of secant squared x, remember the secant squared goes to 1, so this term here, secant squared x, actually drops out, and we can apply the limit to each of the factors. So what we've done between this step here and this step here is separated this quotient to the limit as x goes to 0 of secant squared x times the limit as x goes to 0 of tangent x over x, and then 1/3 in front of both of those pieces. Okay, and so I think I did that wrong. Sorry. That helps better. I think you were looking at my screen here. So the secant squared x, because it goes to 1, just drops out of the equation, and we have this. Notice again that we have 0 over 0. We take the derivative one more time of the numerator of the denominator, and we're left with 1/3. Notice that this time we did a couple things. We applied the rule 3 times, and we substituted that the limit as x goes to 0 of secant squared is equal to 1, so we could just drop that term. Okay? Alright, let's look at one more problem before we go on to the next pieces here. If we apply L'Hospitals Rule, notice the derivative of sine x is cosine x. Notice the derivative of negative cosine x is negative sine x, but it's minus negative sine, so it's positive sine. And here we would get infinity, because as we get closer to pi, x is getting closer to negative. As we get closer to pi from the negative direction, x is getting closer and closer to -1, and sine is getting closer and closer to 0. So we have 1 over a really small number, which is going to infinity, and the fact that it's negative. But wait, something's wrong. Okay? Although the numerator sine x does go to 0 as x goes to pi from the negative direction, notice the denominator does not approach 0. So we forgot to check L'Hospitals Rule here, and this limit is actually easy to find because the function is continuous at pi and the denominator is non-zero. So be careful here. I skipped checking the indeterminate form, and I got an answer that was incorrect because I didn't follow the rules. So that's why I showed you this problem. Okay? You must check the indeterminate form first. Okay? Alright. We can also look at some other way indeterminate. We can have an indeterminate product, and this is when one factor goes to 0 and the other goes to infinity. Okay? So if we had a function that we could write as the product of two functions, and one of them goes to 0 while the other goes to infinity, again, notice we have a contest. We don't know if it's going to 0 faster, is it getting smaller faster, or larger faster, which impacts what's happening with this limit. So what we do here is we rewrite it as a quotient. If we have a product of f times g, notice we can write this as either f over 1 times g, f divided by 1 over g, excuse me, or we could write it as g divided by 1 over f. And then notice here we would actually have the original indeterminate form of either 0 over 0 or infinity over infinity. So here's an example. If we had x times the natural log of x, notice as x goes to 0, x is 0, so this term goes to 0. But as here as x goes to 0, we have a negative infinity. The natural log of 0 is getting to negative infinity. It has to be a really small negative exponent, or excuse me, a really large negative exponent, so that it's becoming a fraction value. So if we rewrite this as the log of x divided by 1 over the other term, 1 over x, notice now we have the natural log of x as x goes to 0 is negative infinity, and as 1 over x is also going to infinity. So we have infinity over infinity, checking the indeterminate form, so we can apply the derivative. The derivative of the natural log of x is 1 over x. The derivative of 1 over x is negative 1 over x squared. When we simplify this, we get simply the limit as x goes to 0 of negative x, which of course equals 0. So when you have an indeterminate product, one factor goes to 0, one goes to infinity, you rewrite it as a quotient, and then you solve it applying LHospitals Rule as we've been doing. We can also have indeterminate differences. Here we would rewrite as a quotient, and this is when we have infinity minus infinity. Okay? So what we'd have to do is to find a common denominator. You'll see this mainly in trig functions, and remember that the denominator of secant is cosine, the denominator of tangent is cosine. So these are sort of set up for us to a certain degree for these indeterminate differences. And these are also more rare, and again, they tend to happen in trig functions or hyperbolic functions. So we rewrite, we have a common denominator, and then we combine it, and then we take the derivative, and in this case we can see it goes to 0. And you can step through this. I imagine this is also an example in chapter 3.7. The last type of indeterminate problem we have is an indeterminate power. Okay, and this is where we have an exponential function, and we either have the base going to 0 and the exponent going to 0, so we have 0 to the 0 power, or we have infinity to the 0 power, the base going to infinity while the exponent goes to 0, or we have a base of 1 while the exponent goes to infinity. Okay, so what we're going to do here is if we have some kind of function, y equals f of g, we're going to write it as an equation. And if we have 0 to the 0, infinity to the 0, or 1 to the infinity, then we can take the natural log of both sides. So notice this equation, this function, we could rewrite as the natural log of y equals the natural log of f to the g. And remember, we can bring the g down in front, and so we get g times the natural log of f. So we can take the natural log and simplify using logarithmic rules. If it's written as an exponential, we can also rewrite it in an exponential form using Euler's constant. So f to the power of g is also equal to e to this natural log here, right? G log f, because e and the natural log sort of cancel out once we put the g back as a power. You need to be able to go both directions with logarithms and exponentials, and this is some key algebraic concepts. Okay, so let's check this example 8. Notice that the cotangent, the sine, let's look inside first. The sine of 0 is 0, and 1 plus 0 is 1, so we have 1 as the base. The cotangent, as we get closer and closer to 0, is an asymptote, so this is going to infinity. So we do have the indeterminate form 1 to infinity. Okay, we must check for the indeterminate form still. We've checked for it. Now we take the natural log of both sides. So first off, we're going to do is we're going to set this equation, this expression, equal to an equation. So we set it y equals what the limit was. Okay. So we take the natural log of both sides. So on the left, I just get the natural log of y. On the right, I take the natural log of this whole thing, and then I bring the exponent down in front. That's all we've done here, is we brought the exponent of cotangent x down in front. This is the power rule for logarithms. All right. Now we're going to rewrite this as a quotient. Okay. So here I have the logarithm, the natural log of 1 plus sine of 4x. That's what we've had here as the numerator, because we have a product here. And remember, when we have a product, we want to rewrite that as a quotient. And cotangent x is 1 over tangent x. So I can rewrite this equation as the natural log of 1 plus 4 sine 4x over the tangent x. Okay. So if I take the if I take the derivative of the numerator, I get this. Remember, this is 1 over the argument, 1 plus sine 4x, times the derivative of the argument, which gives me the derivative of sine is cosine 4x, and then the derivative of inside of this of 4x is 4. So be careful here. This gets a little bit complicated. This is a chain rule with 3 links in the chain to find the numerator. To find the numerator's derivative. The derivative of tangent x is secant x squared. This just simplifies to 4 when we plug in 0, because remember, this is secant goes to 1, sine goes to 0, and cosine goes to 1. So we have 4 over 1, which just gives us 4. Now here's a big deal with these indeterminate powers. Notice we have not solved this limit, because what we're saying here is not that this limit goes to 4. We're saying the limit of the natural log of y goes to 4. And we want to know what y equals, not the natural log of 4. So when we get this, because we've applied the natural log, we have to undo it. And remember, the way we undo it is make this an exponent on e. Okay? So we raise both sides of the equation as the exponent on e. So we get the limit of e to the natural log of y, this is the left side of the equation, equals e to the 4th. Okay? So this is what our answer